Hello, thank you for being here, and thank you to the organizer for giving me the opportunity to present this work. Okay, today I'm going to talk about a tensor network approach to sensing in quantum light matter coupling scenarios. And this is a topic that is very dear to my heart because, first of all, sorry, I want to also introduce my collaborators on this work, who are Ayman and Animesh, but I also want to thank Saurav and Elnaz because they are involved in this project and they've been in all the discussion, most of the discussions. So let's go back to what I was saying. This is a topic that is very dear to my heart because the first motivation is parameter estimation with continuously monitored quantum systems. And the paper on the left is a seminal paper on the field by Gammelmark and Molmer. And here, as you see, this is a picture from this paper. They call this environment, but this is what I will call the emitted light. So here they found a way to compute essentially the sensitivity to parameter estimation of this whole pure state of system and emitted light. And here, if you place a detector, you have your continuously monitored system. But that's the result of this paper was this pure state result. And then this is actually on the right, my first paper on the topic, and it was with my PhD supervisor who is in the audience, Matteo Paris. But I'm also very thankful to Marco Zenoni because he is the guy who introduced me to this field. And this is a picture from this paper. And here already you can see that there's another player, which is this unobserved environment. And basically, I realized that the whole topic today is how to extend this idea of computing these fundamental limits to sensitivity, but now in presence of this unobserved environment, which in the simplest case, is just some inefficient detection. Okay, but the second motivation instead comes from another topic, which is quantum light spectroscopy. I put here this recent perspective from 5 years ago, and this is kind of a topic that has received a lot of hype, but it's quite hard to really understand what are the real fundamental limits into this field. And so this is what we set out to do in Warwick when I was a postdoc with Animesh Datta. And we have a few papers on this topic, but all these papers are essentially in the regime in which there is a single excitation, a single photon that interacts with the matter system, which in this paper was mostly a two-level system. And in this case, we were able also to take into account what happens when this rate gamma perpendicular, gamma perpendicular here was not zero. So there was emission into modes that could not be measured. In this single excitation regime, we were able to deal with that, but we realized that going to coherent state pulses, we didn't know how to do that. We didn't have the tools. So this is why we started to think about this matter. And in both the scenarios I've mentioned, both continuously monitored system and this quantum spectroscopy, the light matter interaction is the usual, let's say, textbook model, where in weak coupling we can describe the electromagnetic field as a quantum noise operator that is delta correlated in time. So this J will be the operator that acts on the emitter, which is a matter system. And we have an incoming pulse of light, which for this talk will be a coherent state. And then the light is emitted, and this is what Molmer was calling the environment in the first slide. And now we have an additional environment, which is Markovian, and again can be described by a Limblad master equation. Of course, tracing out the light, and even without an environment E, this emitter undergoes a Limblad equation. The dynamics is described by a Limblad equation, and that's why Molmer was calling that an environment. But now our main object of interest will be actually the light field and in presence of the environment E. And in particular, we can consider, instead of this Limblad dynamics, a purified version in which these Limblad operators are associated to related noise fields that are called B. So A are the field that can be measured, A is the field that can be measured, and B are the noise field that cannot be measured and are related to the environment. Okay, but now what? The full state is a pure state and evolves formally by solving Schrödinger's equation. But now the problem is quite complex because it's a pure state, but it's tripartite. There are three partitions: the environment, the light, and the matter system. And we only care about the light in the end. This is why we call this spectroscopy in a very, let's say, very generalized way. It's not really just spectroscopical measurement in the common sense, but it's spectroscopy in the sense that you shine light onto the emitter and then you can only measure the light, nothing else. So this is our object of interest. But how to evaluate properties of this emitted light? Well, the standard quantum optics way is just to use input-output and then quantum regression theorem, and then you can compute from the limb light dynamics of the emitter, you can compute correlation functions, spectra, and so on. However, if we take a quantum information approach, this is not enough, because now we need some functionals of the state. It's not enough to evaluate observables and correlation functions. And now, this is much harder, but in absence of this environment, the overall emitter and light state is pure, and there are some tricks that are related to the fact that there exists a Schmidt decomposition for pure states, bipartite pure states, but this is not the case for tripartite systems. So we have to now get, our hands dirty and obtain a more concrete description of the form of this emitted state. So now I don't want you to go through all the details here, but it's just to kind of show that there is a very well established theory about this. And the full state of matter, light, and environment is a so-called continuous matrix product state. And once time is discretized into these discrete time beings, the dynamics can be written essentially as a collisional model. So the emitter sequentially interact with different discretized modes of the field. And in particular, we can also assume that the state initially is pure, and in particular, we can assume that it is in the vacuum. And this also includes a coherent state, because the effect of the coherent state pulse can be mapped onto some time-dependent Hamiltonian on the emitter via the so-called Mollow transform. Finally, after all these steps, what we have in the end is a discrete matrix product state, so a regular matrix product state. And it has two indices, one related to the light field and one related to the environment field. And here, each index can be 0 or 1, related to the fact if there is a photon or not a photon in that particular time being. Okay. Now, pictorially, we can see the matrix product state in this way, and this is the matter system indices, and these are the light and environment indices. And now we can do what I mentioned before. So we can trace out environment and matter system, and we are left with a state in this form. And this is known as a matrix product operator, and in particular, is a locally purified one because you see that the environment is acting on each site separately. And now these matrices here in the matrix product operator are related not to just to these Krauss operators here, but now this is a super operator, a map. So the bond dimension of this state will be d square, where d is the dimension of the emitter system. So, of course, we are not the first to apply matrix product operators in quantum optics. There's a long list, which it's not particularly important in this moment, but it's just to show that it's a very established field. But for what I understand, in most of these papers, people usually care about the matter system dynamics, so the emitter dynamics, and possibly with the effect of coherent feedback, so a very non-trivial non-Markovian dynamics, or just some specific light observables. On the other hand, what we want to do is parameter estimation. And so now I need to introduce the appropriate figures of merit, and I will only give the strictly needed information, even though this is a topic that is also very dear to my heart. So, if you want to talk about it, I'm welcome to chat. But so this is the well-known Kramer bound. So this is a lower bound on the variance of an estimator of this parameter theta. And the first one is the classical one in terms of the classical Fisher information, and the second one is the quantum one in terms of the quantum Fisher information, which is the classical Fisher information optimized over all POVMs for a given quantum state. And okay, so for this talk, this is enough. We can just think about these two quantities as quantifiers of sensitivity for parameter estimation. But when we apply these ideas to continuously monitored system, the situation is a bit more complicated because a continuously monitored system is described by a stochastic master equation. And the computation of the classical Fisher information for this scenario is well known. And also the quantum Fisher, as I explained before, but only in absence of this environment E. So finally, the last ingredient that we need is that for matrix product operators, there is a way to compute efficiently the quantum Fisher information from this variational expression of the quantum Fisher information that is different from the one I've shown before, but is equivalent. And in particular, this is the kind of optimization problem that we need to solve in the matrix operator pictorial formalism. And but it was not obvious for us. Can this work also for a discretized continuous MPO? Because now we have a parameter delta t, and we need to show that this converges also in the limit of delta t going to 0. It was not trivial for us, but it turned out, otherwise I wouldn't be here, that yes, in the end it works, but one needs to be careful about this delta t. And we had to, let's say, perform some non-trivial steps in this existing algorithm. I mean, some non-trivial modifications. But I also want to advertise that simultaneously to our paper, there was another paper by the Plenio group, and in particular the Yu Yang, which solves the same problem in a completely different method. Okay, so finally, just a couple of minutes to present some concrete results. The concrete results are actually in a couple of very simple problems with two-level systems. And the first one is essentially resonance fluorescence. So we have a two-level system with a continuous driving. So this omega is the Rabi frequency, and this is the parameter that we want to estimate. J is the Lindblad operator that we can measure, so the one coupled to the detector. And L is the one related to the noise. So you can see that they are the same, just with a different proportionality constant. So this eta is just the proportion of light that is the efficiency, essentially, the proportion of light that can be measured. And here you can see that the black line was the existing bound from the two-sided master equation, and the circles are the new computation using MPOs, while the stars and the diamonds are photo detection CFI and homodyne detection CFI. And we see that in the regime of small RB frequency, these are almost optimal, while it ceases to be the case for longer times, if we evolve for longer. And if we go to larger, it ceases to be the case if we go to larger Rabi frequencies. And similarly to this continuous driving case, we can also consider the pulsed case, which is what originally motivated us. And here you can see that the problem is essentially very similar, just we have a slightly different parameterization, and now the Hamiltonian is time dependent, and there is this Gaussian pulse. Okay, I'm about to finish, just 30 seconds. And basically, we can compute also all the quantities in the pulse scenario, and we can see that we compare them on a per photon basis with the single photon results with the same wave packet. And we can see that for large losses, there is a bigger gap. And this couldn't be seen with previous methods. So now these are the conclusions, but I will just skip very quickly. And yeah, I thank you for your attention. Sorry.
Thank you very much. And we have 1-2 minutes for a few short questions. We don't have. So I wonder that the method is analogous or similar to the transverse matrix method in optics, where you, for instance, shine on some object and then calculate in slices propagation, and then again multiply all the matrices to get the output?
I think so, even though I'm not aware of a formal connection, but I would like to look into this. I didn't think about this.
No more questions? So thanks the speaker again.